Brilliant. All right, thank you very much. And thanks to the organizers for giving me the opportunity to talk about this today. My name is Callum Bellhouse. I'm a postdoc at the ENAF Observatory of Padova. And I'm going to be talking today about an interesting morphological side effect, let's say, of ram pressure, an unwinding effect that's been observed in several jellyfish galaxies observed in the GASP program. So to give some context to what I'll be talking about today, I'll give a very brief background on ram pressure stripping. So ram pressure was first discussed by Gunn and Gott back in 1972. And the simple model boils down to this, that a galaxy moving with a sufficient velocity through a medium of sufficient density will experience a drag force which acts upon its gas component. And if that drag force is sufficiently large to overcome the galaxy's restoring force, that means the gas component will be stripped. And this can have fairly spectacular morphological consequences. What we generally see is in observations is the formation of tails behind the galaxy along the direction of the wind. And in some cases, a bow shock on the leading edge of the disk if the force is particularly strong. We often see an initial boost of star formation, and then eventually the galaxy becomes truncated and the star formation is quenched. And what we're really interested in is sort of more in-depth look at these sort of initial stages, how the galaxy is behaving, the processes ongoing in the disk and in the tails as that material is removed and begins to form stars. And we want to know things like what is the fate of the stripped gas and how ram pressure behaves as a function of various other parameters. And this is where GASP comes into it. And I won't say too much about this because Bianca's going to be talking tomorrow. This is a Muse large program PR'd by Bianca Porgianti. And just to give enough background to give some context to my talk, the GASP catalog comes from an original sample of 419 galaxies from Omega Wings, and PM2GC. And these were selected using B-band images to look for any signs, for example, debris tails, strip material, and asymmetries, to find any signs of visual signatures of ram pressure stripping. And from this sample, we have 94 homogeneously selected ram pressure stripped galaxies, all observed with Muse. This fantastic mosaic on the right, put together by Marco, gives a great overview of all the galaxies that we have. And this, we can switch between the visual, the RGB images made from the Muse and the H-alpha, which gives a really detailed picture of the stripping. So the GASP sample is selected to range across different stellar masses, different environmental densities, and to give us very detailed information on each galaxy with the fantastic Muse data, but also a statistically significant sample to study various different relations. So the story that I'm going to be talking about today starts with the jellyfish galaxy JO201, which is a particularly interesting galaxy that constantly throws us new curveballs, including this entire process here. So JO201 lies within an infalling group. It's in a large cluster Abel 85, and it's moving at an exceptionally large line of sight velocity, so 3 times the cluster sigma towards the observer. And what's particularly interesting about JO201, or one of the many things that's interesting about JO201, is that it appears to be not only stripping, but also unwinding. And sort of in contrast to our conventional picture of jellyfish galaxies, where we see these nice kind of tentacles and trails lining up behind the galaxy, JO201's stripped material, the knots and blobs of star formation, appear to be aligned with the spiral arms of the galaxy. And we also see this, so we first picked this up in the H-alpha with these knots of material that are all a very similar redshift to the galaxy, slightly redshifted due to the ram pressure stripping. But having noted this, we then spotted the same kind of effect in 10 other jellyfish galaxies in GASP. And what's interesting is it's visible in galaxies not just undergoing stripping face on to the wind, but also edge on with respect to the wind. And more detail on this this whole study is given in Bellhouse et al. 2020 if you want to have some background reading. So looking at the sample in phase space, we have here the cluster-centric radius of each of these galaxies and the velocity with respect to the cluster center. And each of these galaxies has been plotted as a thumbnail image centered on its location in phase space. So this gives us an idea of the distribution of the morphologies of these galaxies throughout the cluster. And what we can see is firstly that these galaxies aren't particularly located in any region of phase space, but they do tend to avoid the centermost virialized region. We further separate these galaxies with the gray contours into galaxies that are more likely to be moving on the plane of the sky and galaxies more likely to be moving along the line of sight. So this is using simulations of 42 different clusters observed from 50 lines of sight. We produce a grid to determine the most likely velocity angle of a galaxy based on its location in phase space. So galaxies within this gray area are more likely to be moving on the plane of the sky, and galaxies outside of the gray region are more likely to be moving along the line of sight. And that's interesting that coupled with their face-on inclinations to the observer, these galaxies are more likely to be moving, to be stripped face-on with respect to the intracluster medium. And what we find is that the galaxies more likely to be undergoing face-on stripping tend to be more symmetric. The unwinding appears to be occurring all around the edges of the disk, whereas the edge-on strip, the galaxies moving edge-on with respect to the ICM, are more undergoing asymmetric unwinding. So we tend to see galaxies like JO93, JO194, and JO85 tend to have the unwinding effect on all sides, in contrast to JO200, JO49, JO175, where the unwinding is particularly to one side of the galaxy. We then look at the stellar kinematics, comparing the gas kinematics and the stellar kinematics. So the H-alpha kinematics from emission line fits and the stellar kinematics from absorption line fits using PPXF. And we generally find that the H-alpha kinematics show that the unwinding component is rotating consistently with the rest of the disk and is not hugely deviated from the disk velocity. The stellar kinematics in both cases show, or in all cases of these galaxies, show very little major disturbance. So the stars continue to rotate as normal. And this is expected for a ram pressure stripping process as opposed to tidal effects, since ram pressure affects only the gas component of the galaxy. So what we're seeing is that the stars remain completely undisturbed. Whilst in a gravitational interaction, we'd expect the stars to be disturbed in the same way as the gas. And dividing the stellar component into old versus younger stars, we can see that generally the older stars within the disk completely confined to the disk region of the galaxy, whereas the younger stellar component, the youngest stellar component, stars less than 2 × 10⁻⁷ years, tend to be following that the H-alpha emission and the unwinding arms. So these are galaxies that are most likely to have formed in situ in the tails after they've unwound. So again, this is consistent with ram pressure stripping, that we see the older stellar component confined within the disk and the young stellar component tracing the new tails. So the next thing we looked at was manually identifying the spiral arms and measuring the pitch angles to understand the radial dependence of the pitch angle and see if this is a physical unwinding effect or just an apparent effect because of the extended spiral arms due to stripping. So we located spiral arms manually in, this is showing an unwrapped polar space of the galaxy corrected for inclination. And so spiral arms appear as straight lines on this side. We obtained the inner and outer pitch angles for each galaxy. So within, we defined 2 times the stellar disk scale radius and measured the pitch angles inside and outside of that, both for the stripped sample and for the control sample. And this gives us the radial dependence of the pitch angle. And what we find is that in the control galaxies, the pitch angle is generally constant from between the inner and outer disk, whilst the pitch angle in the stripped sample is consistently higher outside in the outer regions of the disk and out in the tails compared to the inner regions. So this shows that it's a physical unwinding effect. It's not just an apparent effect due to the extended spiral arms. We then compared the observed galaxies with a series of high-resolution wind tunnel simulations of an edge-on and face-on stripped galaxy. So this figure here shows the JO200, one of our sample, compared with a simulated edge-on stripped galaxy that's been rotated and angled to give a similar viewpoint as which we observed JO200. And you can see this very nicely mimics the unwinding effect in JO200. The mass of the galaxy is slightly different, so we have a slightly different velocity scale, but in general, the unwinding effect is appearing in a very similar way to that in JO200. And these simulations give us the chance to look at the unwinding process throughout the infall. So we break this into different time steps through infall, and we can see that for the Edge-on galaxy, the unwinding effect becomes apparent fairly quickly after infall. About 81 megayears after first infall, we start to see this fantastic pileup of material on the right-hand side. The wind angle, note, and this is downwards and out of the screen. So this galaxy is moving up and into the screen, into the wind. We then find that this unwinding starts to wash out around 416 megayears, and eventually by 789 megayears, this galaxy appears more like a sort of conventional jellyfish galaxy with the more collimated tails directly behind. Comparing this to the face-on simulated galaxy, we find that similarly, the unwinding is less prominent, but arises in a similar timescale. We can start to see the unwinding around the edges of the disk. And what we find is that generally the material removed from the outer edges of the disk starts to fall to higher radii as it's removed from the gravitational potential. And in a similar way, this slowly washes out and becomes less visible. And by 789 megayears, we end up with a very sharply rotating, very truncated disk with nice long jellyfish tails. So to look at those two different processes in a bit more detail, for the Edge-on stripped galaxy, we can see that, the color on this shows the 2D velocity. What we find is that the material that's moving in the same direction as the wind doesn't take much additional velocity, additional kick from the ram pressure to remove it completely from the disk. Thank you. Whilst the material that's moving into the wind it takes a lot more to be stripped, and it's in this early stage of ram pressure stripping is initially slowed as it moves into the wind. So what we find is that a lot of the gas is being removed from the side that rotates with the wind, and eventually, if it continues to orbit around the galaxy, it encounters this traffic jam of material as it comes back around the other side. And what's interesting as a sort of side effect in this case is that the result of this is that a lot of the material, based only on the distribution of material here, if you were to select a direction that you would expect this galaxy to be moving, most of the tail is along this way. So actually a hand-drawn tail for this galaxy would be misaligned by 30 to 45 degrees from the true wind direction in this case. So that's just an interesting kind of health warning for measuring tail angles, limited specifically to these kind of early infall cases where galaxies are particularly unwinding. The rotation can actually kick the tail around much further than the wind direction implies. And then in the face-on stripped galaxy, we can see this is taking slices further and further downwind of the galaxy. The outside end stripping removes gas from the outer edges of the disk first, and then consecutively more inward. And as that gas is removed from the disk potential, to conserve angular momentum, it falls to higher radii. And as it's completely stripped, it continues to move tangentially. So what we see is this material is kind of removed. If we imagine a ring of material being removed from the outer edges of the disk, that's eventually removed from the potential and completely flung out. So we sort of see this unwinding from the viewed from the top down as the material falling away from the galaxy. And this gives us the symmetrical unwinding effect that we see in some of our other galaxies. So we expect these two different models, these kind of put together quite a nice picture that explains the galaxies that we have in our observed sample. And we expect, depending on the inclination, different combinations of these effects to be leading to unwinding in the galaxies that we've looked at. And so in conclusion, we confirm this unwinding effect in several galaxies within GASP. And we also confirm that it's indeed a hydrodynamical effect that's traced by gas and young stars, and also backed up with simulations that use purely hydrodynamical processes. And we use that to identify two different processes depending on the inclination of the galaxy. And finally, we find that the unwinding occurs fairly early on in the infall process and then washes out to give way to more conventional signs of ram pressure. So thank you very much.